Hello again. So far, we've assumed that productivity change is something that occurs exogenously. Now it's time to think a little bit about why it is that productivity might increase over time. What are the economic mechanisms that might cause this phenomenon? We're going to start by looking at the class of growth models that I'm going to call ideas-based growth models. These are going to be models where productivity change occurs because of the accumulation of knowledge. And the class of models that we're going to look at is sometimes referred to as the semi-endogenous growth models. The reason they're called semi-endogenous growth models, as we'll see, is that the ultimate driving force of growth in these models is going to be that there is an increase in the number of researchers over time. To put another way, just like in the context of AK models, where we require linearity of some kind in order to get endogenous growth, here, in the case of ideas-based growth models, we're also going to require linearity in order to get endogenous growth in an environment where the population isn't growing. That version of the model, however, is going to have a prediction that does not fit with reality, which is the idea of scale effects. That a larger economy will actually grow faster than a smaller one, and if there were population growth, or more generally growth in the resources devoted to research and development, then growth would accelerate. Of course, we don't see that. And so that tells us that there must be some decreasing returns somewhere in the production function for generating new ideas. And once we have decreasing returns there, what it does is it means that the ultimate driving force of growth turns out to be population growth, or again, more generally, growth in the amount of resources devoted to R&D. Let's take a look. Now, one thing that it's probably worth pausing to think about is what are the desirable properties of a model of economic growth? Now, one is that, of course, it should fit salient facts about economic growth, such as the balanced growth path that we observe in the case of the United States. And I'll talk a little later about how it is that this idea applies quite generally, even when there are growth miracles. Second property is, of course, that it should be consistent with other data. Now, this is different. Point one is about broad facts about growth. But point two is about predictions that stem from that model. So, for example, in the case of AK models, growth comes out of having more capital. And so a prediction of these models is that investment causes growth, ergo, economies that invest a greater share of their GDP should grow faster. And a paper by Jones in 1995 shows that the data do not support this. So aside from any feelings or thoughts we may have had about knife edge conditions, such as the curse of linearity, making a model good or not, ultimately, we are scientists, and it's the data that tell us whether or not our models are good. So we start from some features like balanced growth, use that to build a model, and then in a second stage, we check the predictions of that model that go beyond where we started. In the case of AK models, it doesn't work. So we need to go somewhere else. And this is what motivated a different kind of model called the R&D-based growth models, or the ideas-based growth models. Now, this literature came out of the work of Paul Romer, who in a wide-ranging paper in 1990 introduced many of the ideas that were going to lead to this new class of models. And some of the things that motivated him are not essential for that literature, and some are. I'm just going to present some of his ideas, and then later we'll figure out what is or isn't essential. So he started from the observation that the kinds of commodities, goods, resources like capital that we exchange and think of in economics have two properties. One of them is that they are rival. And that means that if I have the thing or am using the thing, you can't simultaneously use it. I could have a thing and then give it to you if it's durable for you to use it later, but we can't both use it at the same time. That's rivalry. A concept that you may have talked about in Econ 1 as an undergraduate. In addition, typical goods are excludable. And that means that if a thing is mine, then you can't take it. The concept of excludability is something that I think maybe is taken too much for granted because, of course, there is theft. There is expropriation by other agents, including possibly the government. So excludability, if you really think about it, has to be an imperfect concept. But now let's think about ideas. An idea, which I guess you can think of as a piece of knowledge about something. And of course, since this is an economics course, it must be about something economically useful. Ideas are different. Ideas are non-rival. And that should be clear. I am sitting here telling you things that you didn't know. That's why this is a class. You will take that knowledge and use it for your purposes to hopefully develop groundbreaking research. And I can use the same knowledge and develop groundbreaking research as well, in different directions, hopefully. Well, if it's in the same direction, then we should talk and collaborate. In any case, in that sense, ideas are non-rival. Multiple people can use the same knowledge. And I guess in that hint that I just gave, you can see why the fact that ideas are non-rival could potentially cause problems, because what if I incurred costs coming up with some knowledge, but you could take the knowledge costlessly from me and use it? That would be a problem. It would be a problem in the sense that it would make it hard to reward the production of ideas. Anyhow, ideas might also be less excludable. This isn't so central here, but it's still worth thinking about. I can exclude you from my ideas by not telling you about them. But of course, it could be that you are able to learn about my implementation of ideas by, let's say, reverse engineering whatever it is that I built using my new ideas. In addition, excludability is a bit of a more slippery concept because, as discussed, it probably has something to do with the legal system. For example, patents and other forms of intellectual property rights, such as trademarks, copyright, and registered designs, might effectively preclude someone else from using my ideas, which of course makes them more excludable. That means excludability is a very interesting concept that has a lot to do with institutions. But in any case, ideas are non-rival and maybe less excludable than typical goods. Building on that, let's try and construct a model of economic growth. First, propose that having decided that AK models can do the job, so we need some kind of long-run productivity change to get growth. Growth is due to the accumulation of ideas, not the accumulation of objects, such as capital, or human capital for that matter, physical or human. 2, ideas are not rival. So that means that potentially multiple people may benefit from the use of the same idea. Now, let's write down a model that has these ideas, has these concepts embedded. Let's start with output being a product of the number of ideas. So now productivity is going to be related to the number of ideas, and we're just going to call it A, just to pick a letter out of a hat, times NT. So we're going to forget capital because we're not interested in it. We're interested in the dynamics of ideas. We could put capital back. It's just going to complicate things unnecessarily. So labor is the only input, and it's not reproducible. In addition, we have the possibility that resources can be used to produce ideas. So if A is the number of ideas, then new ideas is AT plus 1 minus AT. We could have a depreciation rate, but let's not worry about that right now. And that equals, or that is related to, rather, this, which we're going to call labor devoted to research. Now, this could be either some share of the total labor endowments of the economy, or it could just be a separate kind of labor that's available in a fixed quantity. For simplicity, let's just go with that, since the point here is just to get the basics of the model down on the table. So it's related to research labor, or research input more broadly, I guess, times some number, which let's call for now delta tilde. The next question is, what factors might affect the marginal productivity of research labor? Or in other words, what is delta tilde? One possibility is that delta tilde could itself depend on the number of pre-existing ideas. This, for example, is in another Jones paper. Well, They're both in 1995, so let's call this one Jones A. Let's call this one Jones B. Then we have delta tilde equals some number delta times A to some power, which I'm going to call phi or phi. And then this equation, of course, becomes this. And in this context, there are two possibilities, I guess. Well, there are three. One is that phi is bigger than 0. Then the more ideas you have, the easier it is to make other ideas. We call that standing on shoulders, which is a phrase that originates from a quote often attributed to Isaac Newton, something along the lines of, if I have seen further than others, it's because I was standing on the shoulders of giants. I read somewhere that he got that idea from somewhere else, but anyway, standing on shoulders. I guess he was standing on other people's shoulders if he took their quote. Another possibility is phi less than 0, which is called fishing out. I guess the idea there is that there's some fish that are easy to catch, and once you've caught them, catching the next fish is harder because there's fewer of them. Something like that. The third possibility, of course, is that phi is 0, which means that, well, it's not a problem for the literature if phi is 0. It just means that the amount of pre-existing knowledge doesn't affect how hard or easy it is to come up with more knowledge. I argue that trying to figure out which case is relevant for the world is important. Now, another possible factor that we might want to take into account here, however, is the idea that there could be duplication. In other words, these researchers here aren't necessarily working on different things. They could be working on the same thing, and the more they work, the more they're likely to overlap, which means, of course, that there are decreasing returns to R&D. In that case, we would argue for a delta tilde that is, well, affected by pre-existing knowledge in the way described here, but which may also be decreasing in research input. And if we go with that case, then we're going to have this as our production function for ideas. Now, there should be a general equilibrium model written around this whole thing to make sure that everything works, that resources are used, markets clear, and so on. But I'm going to follow the guidance of Jones B, where the main text focuses on what we're discussing now. And then in the appendix, there is this sort of full general equilibrium model where all of this works out. So that we can jump straight to the crunch here. Suppose there is a balanced growth path in this model, and let G of A be the growth factor of A. And now let's take a look at this. If we divide both sides by A, we get, of course, the growth factor of A is this divided by this. So we get G of A minus 1 is equal to this function. Now, let G of L be the growth factor of LA. Why might LA grow? Well, maybe it doesn't grow, or maybe it grows if there's population growth. Then this thing is going to transform itself into the following. We're going to have that this is some A0 where we started with by G of A to the power of T. And this is going to be some L0 times G sub L to the T. So we'll have this equation. And the point is that this, if we have a balanced growth path, is a constant. This, on the other hand, grows, or rather, some of its elements grow. That means that in order for this to be a constant, whatever grows here must cancel out. So whatever growth this implies for what's on the left-hand side must be exactly canceled out by whatever growth this implies for what's on the left-hand side. And that means that this must equal the opposite of this. So one of these needs a minus. I'm just going to put it here. And finally, what does that give us? It gives us that G of A equals G of L, this power. There we go. So in Jones, who has population growth, just like some of the models we considered earlier, if population growth equals this GL, which would make sense in the long run, since presumably we'll have in the long run some sort of constant of this. So one of these needs a minus. I'm just going to put it here. And finally, what does that give us? It gives us that G of A equals G of L, this power. There we go. So in Jones, who has population growth, just like some of the models we considered earlier, if population growth equals this GL, which would make sense in the long run, since presumably we'll have in the long run some sort of constant share of the labor force that's devoted to research, then this will be growing with the rate of the population growth. And that will ultimately lead to there being more and more ideas. Now, in the Romer paper, phi equals 1. So this thing is undefined. On the other hand, in the Romer paper also, there is no population growth. And so in his model, the problem is that if you have population growth, then, well, this equation would suggest infinite growth. And more broadly, if you look at this paper, what the possibility of an increasing population means, because there are no decreasing returns through R&D, is that the more people you have, the faster you grow. Countries with radio populations should grow faster, or more generally, as the globe accumulates more people and more researchers, growth should accelerate. And of course, we don't see that. So that invalidates the particular parameterization of Romer's paper, but it doesn't invalidate the ideas. Jones 1995b shows us that introducing decreasing returns gets everything back under control. This is known as the scale effects problem, and any good model of economic growth needs to make sure that it doesn't experience this scale effects problem, which means that this should not be the case that larger economies grow faster. For example, in Romer's case, what it means, the way it's set up, is that because feet in the Romer case is equal to 1, it means that basically if you have a larger amount of researchers, you will actually end up with faster growth. That's the scale effects problem. Of course, if you are someone who was interested in understanding growth policy, how growth might be affected by something or other, that would seem to indicate that you should just try and get more and more people to do research, and you'll not just get more GDP, you'll get faster and faster economic growth. And of course, the only reason for that is because your model has scale effects. And so we can't reach that conclusion. There's a problem with your model. So the scale effects problem is something to keep in mind whenever you evaluate any sort of endogenous growth model. Your model must not have scale effects, and there should certainly not be any policy implications that are there just because you have scale effects. Now, I said something earlier about excludability. Let me give you a model that's similar to this that introduces that notion. So far, we were not thinking about who this knowledge belonged to, but let's expand that. Suppose we take this ideas production function, and now suppose there's a distinction between my knowledge and let's call it public knowledge. And let's say that public knowledge is a bar, T, and let's just say that it's the average. Then let's say that this impact of knowledge on the productivity of future knowledge is actually split between my knowledge, which is AT, and public knowledge, which is a bar. And let's say public knowledge is affected by a spillover parameter, which I'm going to call sigma. In this formulation, phi is telling us what is the overall intertemporal knowledge spillover, standing on shoulders, fishing out. And then sigma, which we're restricting to be between 0 and 1, tells us how much of it is a spillover from my own knowledge versus spillovers from other agents. In this way, you could have excludability essentially in the form of this sigma. Excludability in terms of how much you can use other people's knowledge to produce new knowledge. It's very important, and I guess this is why I mentioned it in the first place, though there's a different kind of excludability, which is the ease with which I can use your knowledge to produce goods as opposed to new knowledge. These are two different things, right? One is to be able to access your knowledge so I can make progress. Another is to access your knowledge so I can make products. So all of these notions are nuanced, and I think those nuances all open interesting avenues for research. Another possibility is that so far we've assumed that these ideas show up here in the production function. But maybe that's not the only place where ideas can show up. Consider the alternative possibility. Remember that when we talked about sources of growth, we had the regular capital accumulation production function, which looks like this. When we were talking about sources of growth, we introduced the possibility that the efficiency of the investment process could itself change over time due to investment-specific technical change. The amount of resources that you take away from consumption and instead devote to investment could increase in efficiency over time, which again could be viewed simply as having two sectors, consumption and investment, where the investment sector experiences more rapid technical progress. Now let me just replace this letter Q with the letter A. Now suddenly we would have ideas-based investment-specific technical change. This is something the literature hasn't looked at very much, but one paper that does is Crusoe 1998 in the Journal of Economic Growth, which ultimately is sort of a distillation of his dissertation, which is fun to read. And I looked at it a little bit in a paper in macroeconomic dynamics, but I feel like there may be more here to be uncovered, because maybe our view of where the ideas show up in our macroeconomic dynamics isn't right. Maybe it's not in total factor productivity, rather it's in investment-specific technical change. And what this opens up more broadly is the idea that, of course, the ideas could be showing up in all sorts of places, because it's just a fact that we have many industries, not just capital and consumption, but a whole bunch of other ones, right? There are all sorts of different industries, and maybe we should be trying to aggregate up the contribution of each to the production of knowledge. And one such paper that I can think of just off the top of my head that tries to do that is, well, I have one with Rachel Nye in the Review of Economic Dynamics, but I think a really interesting contribution is by Tsai and Lee in the Review of Economic Studies, which takes seriously the possibility of spillovers of knowledge, not just across agents, but across industries. And of course, that's a very complicated matrix, and they work with it and develop a series of very interesting results.